Hello, in this short video I'll be introducing you to SI base units and derived units. As we can see here, there are loads of different units available for measuring quantities in physics. We need to get our head around the difference between base units and derived units and understand which units are SI, in other words, the units that we should use whenever we're doing calculations in physics. There are 7 units we call the SI base units. These 7 units can be used to form any other unit used in physics. They are the meter, used to measure distance, kilograms for mass, seconds for time, Kelvin for temperature, the ampere for electrical current, the mole measures the quantity of something, and the candela is a unit of luminous intensity. What about if you want to measure the speed of something? Well, for that you would need to use a derived unit. And to derive the unit for speed, we need to know the equation for speed. We know that speed, v, equals distance divided by time. So now we can put these units into this equation to find out what the unit for speed will be. So the unit for distance is the meter. The unit for time is the second. So our unit for speed must be the meter per second. Note how I've written it in line. It's usually good practice to write physics equations in line like this rather than as a fraction. The s to the minus 1 here just means 1 divided by s, so it is the same as writing this, but it is a neater way of writing it, especially when we get onto more complex units. Speaking of more complex units, what about if we want to find the unit for force? Well, the equation F equals ma, force equals mass times acceleration can help us here. We know the unit for mass is the kilogram. However, we don't know the unit for acceleration. So let's begin by working that out. Acceleration equals the change in velocity divided by the change in time. The triangle there means that is the capital Greek letter delta. It means change of. Since we already know that the unit for velocity is meters per second, we can write that in here. And because we know that the unit for time is the second, we can add that here. And that is the same as writing meters per second squared, or meters seconds to the power of minus 2, which is a neater way of writing it. So now we have the unit for acceleration, and we know the unit for mass. So let's plug this into F equals ma. So F equals ma. So the unit for mass equals kilogram. The unit for acceleration is meters seconds to the minus 2. So that must be our unit for force. Now that might surprise you because you've been used to using a different unit for force, the Newton. Which brings us neatly onto derived units. It would be very clumsy every time we wanted to measure a force if we wrote the units as kilogram meters per second squared. So we've given names to many of these derived units. These are just some of them. The Newton, as we've just seen, is equal to 1 kilogram meters seconds to the minus 2, or meters per second squared. It's a mass multiplied by acceleration. So 1 Newton of force is equal to 1 kilogram meter seconds to the minus 2. What about a joule of energy? Let's see how we'd work this out. So the equation for work done is the work done by a force equals the force multiplied by the distance moved in the direction of the force. Now we know that the unit for force, the Newton, expressed in base units only, kilograms, meters and seconds in this case, is kilogram meters seconds to the minus 2. And we know that the unit for distance is the meter. We can simplify this to kilogram meters squared seconds to the power of minus 2. So the unit for work, the joule, is equal to 1 kilogram meters squared seconds to the minus 2. We can do a similar exercise to work out what a hertz, a pascal, and all the other SI derived units are. While we're talking about units, let's look at some conventions. You'll notice that all of the units have a lowercase first letter. You must never write the word of a unit in capital letters. However, sometimes the symbols associated with the units will have a capital letter, and there is a pattern for this. The Newton has a capital N, the Joule has a capital J, the Hertz has a capital H and a lowercase z, and the Pascal a capital P and a lowercase a. Now, what all four of these units have in common is that they are named after a person. So they will have a capital letter in their symbol, though not in their word. If we return to our base units, you'll see that the meter is written with a lowercase m, the kilogram, lowercase kg. It's worth pointing out here that the gram is not the base unit of mass, so we've added a prefix to it to make it the kilogram. That's the only example of a base unit that has a prefix, saying it's 1,000 grams. The second is a lowercase s. Kelvin is an uppercase K because the Kelvin is named after Lord Kelvin, whereas the meter, kilogram, and seconds are not named after people. The ampere is also named after a person, so it's a capital A. The mol is lowercase mol, and the candela is a lowercase c d.